You know that feeling when you like hear or sense something that seems a bit off in a complex system.
Yeah, like hearing a note that isn't actually being played.
Exactly. Or maybe you feel a weird vibration in some machinery, but it just doesn't line up with how fast it's running. It's like signals are just showing up out of nowhere.
Uh-huh. Not directly linked to the main inputs or what you expect to be driving things.
Precisely. And that's what we're really digging into today, this whole idea of ghost frequencies and ghost resonance.
These are signals or maybe responses that crop up in places you wouldn't normally predict, just based on the system's basic setup or the obvious inputs.
For this deep dive, we've got two really interesting sources lined up. One is more on the fundamental physics side,
Right. It looks at this phenomenon in a classic electronic circuit, one that's actually known for behaving chaotically.
and the other source, totally different world. It's a real-world engineering case study. It talks about how they use this specialized vibration analyzer to track down a similar kind of unexpected frequency issue in some big industrial machines.
So our mission here is basically to unpack these two sources. We want to understand, what is ghost resonance? How does it pop up in such different systems like a lab circuit versus a huge compressor?
And crucially, why should you care about these weird, unexpected signals, whether you're thinking about electronics, big machines, or maybe even how our own bodies process information?
Yeah, it turns out these ghost signals can tell us a lot, sometimes revealing hidden stuff about the system, other times causing real problems.
So get ready for some pretty surprising insights, I think, into how complex systems tick and how they respond to the world in ways that aren't always obvious. Let's jump in.
Okay, so starting with the physics side, it's really fascinating how scientists try to get a handle on these complex systems. They often poke them, see how they react to things like noise or really intricate signals.
Right, and that connects to something called stochastic resonance, doesn't it?
It does, yeah. Stochastic resonance is this kind of mind-bending idea. It suggests that adding a bit of noise, random fuzz to a system can sometimes help it pick up on a really weak signal it would otherwise miss completely.
Which totally flips the usual script, right?
Right.
Usually noise is just noise. It gets in the way.
Exactly. But here, it can actually be constructive. And ghost resonance is, let's say, a cousin to that idea. It involves frequencies showing up in the system's output that weren't deliberately put into the input.
Like that missing fundamental thing in audio.
Perfect example. You hear tones at, say, 200 hertz, 300 hertz, 400 hertz, maybe just the harmonics. But your brain often kind of fills in the blank and perceives the bass note, the 100 hertz fundamental, even if it's not physically there in the sound wave.
Ah, okay, so your brain conjures up this ghost frequency based on the pattern.
Precisely. And scientists see similar things happening in models of neurons and other complex systems. Now, this first paper we're looking at explores this very phenomenon in a really well-studied electronic setup,
Yeah.
the Chua circuit.
Oh yeah, Chua's circuit. It's pretty famous in chaos theory circles. It uses like standard resistors, capacitors, inductors. But the key is this special nonlinear component.
That's the one, sometimes called Chua's diode. That little nonlinear element is what lets this relatively simple circuit do all sorts of complex, chaotic things.
And for the study, what aspect of its behavior were they focused on?
They were looking at its ability to sort of flip between different chaotic states.
Hmm.
Imagine it switching between two distinct modes of oscillation, often called attractors.
Okay, like it prefers one pattern or another, and it can jump between them.
Right. And there's a certain minimum signal strength and amplitude threshold that an external signal needs to have to reliably make the circuit jump from one state to the other.
But here's the kicker, and this seems really important from the paper. That threshold isn't the same for every signal, is it?
No, absolutely not. It changes depending on the frequency of the signal you're feeding in. A signal at one frequency might need less amplitude to cause a jump than a signal at another frequency.
Got it. So the circuit is kind of biased. It's easier to push over the edge at certain frequencies.
Exactly. And that frequency-dependent threshold is key to understanding how the ghost resonance appears here. So first, let's think about what happened when they used a weak signal.
Okay, weak meaning below that threshold needed to cause the jumps on its own.
Right. A subthreshold signal. And this signal wasn't just one frequency. It was complex, made up of multiple frequencies. Then on top of that weak signal, they added random noise.
Ah, so bringing in the stochastic resonance idea, the noise gives the weak signal the extra nudge it needs.
Precisely. The noise helps the system cross the threshold and jump between states. And here's the really cool part. When they looked at the circuit's output signal, what it was actually doing,
Ah.
They saw a clear spike, a response, at a frequency that wasn't in the input signal at all. It was responding at the missing fundamental of those input frequencies, the ghost frequency.
Wow. So the noise helped reveal this hidden frequency response.
Yes, but there was a slight snag initially. Remember that frequency-dependent threshold?
Uh-huh. Easier to jump at some frequencies than others.
Well, if they just made all the input frequency components have the same amplitude, the circuit naturally responded more easily to the frequencies that were already closer to their individual jump thresholds.
Ah, so the response wasn't clean. The ghost frequency signal was maybe weaker or muddied because the circuit was playing favorites with the input frequencies?
Exactly. The signature was weaker, maybe a bit off target compared to what theory predicted. It
Uh,
was there, but not as clear as it could be.
Okay, so how did they fix that? How did they get a clearer picture?
This was pretty clever. They decided to tailor the input signal instead of equal amplitudes for all frequency components.
They adjusted them.
Yes, they adjusted the amplitude of each frequency component based on how hard or easy it was for that specific frequency to make the circuit jump. They basically leveled the playing field.
So they compensated for the circuit's own frequency biases?
Precisely. By making the input amplitudes proportional to the individual frequency thresholds, they ensured, with the help of the noise, that all input components had a more equal chance to influence the jumping behavior.
And the result.
Much better. The ghost resonance signature in the output became much stronger, much sharper, and it lined up really well with the theoretical predictions.
Okay, that makes sense for weak signals getting a boost from noise. But what about without noise? The paper asked if this could happen just with a strong signal, right? One that's already above the threshold.
Yes, exactly. Can the circuit generate this ghost frequency just from its own internal chaotic dynamics when driven hard enough without needing external noise?
And could it?
It could. When they drove the circuit with a signal strong enough to cause the state jumps on its own, a superthreshold signal, it still showed a response at the missing fundamental frequency.
Really? Even without the added noise?
Yep. For example, hitting it with signals at 60 hertz and 90 hertz, both strong enough, resulted in a clear output response peak at their missing fundamental, 30 hertz.
So the circuit's own chaotic swishing behavior can somehow enable this phenomenon.
It seems so in this context. The paper did note, though, that this non-noise-assisted ghost resonance was clearest when the driving signal was strong enough, sure, but maybe not massively strong, kind of in a sweet spot just above the threshold.
Interesting. And did they try this with more complex signals too, like multiple frequencies above the threshold?
They did. They tried it with 4 components. And again, if they just used same amplitude components, the ghost frequency response didn't quite match the standard theory, especially for an even number of inputs. That frequency-dependent threshold bias was still messing things up.
So, same solution. Tailor the input signal again.
You got it. By scaling the amplitudes of those super threshold input frequencies based on the circuit's known frequency-dependent threshold, they could get the output ghost frequencies to match the theoretical predictions really well.
Okay, so pulling back from the circuit details, the big takeaway from this physics source seems to be that ghost resonance isn't just some weird artifact. It's like a fundamental behavior of these nonlinear systems.
Yeah, it seems baked into how they work. It can happen with noise, helping a weak signal, or even without noise if the signal's strong enough.
And critically, the system's own quirks, like how it responds differently to different frequencies, play a huge role. You almost have to understand and account for those quirks to really see or use the ghost resonance clearly.
Absolutely. It shows these systems aren't just simple amplifiers. They actively transform signals in complex ways, sometimes creating entirely new frequency content out of thin air, so to speak.
Okay, that's a fascinating look from the fundamental physics angle. Now let's pivot completely. The factory floor, basically. Big, heavy, real-world machinery.
Right. Our second source is this white paper about diagnosing vibration problems in gas compressor trains. These are huge systems, motor, gearbox, compressor, pushing natural gas around. Super critical infrastructure.
And monitoring their health, especially vibration, is key. But I guess getting good data from something that big and complex is a challenge.
It definitely can be. You often want measurements from multiple spots at the same time, and doing that sequentially can take ages and might miss things that are happening simultaneously.
So what was the key piece of kit they used here?
They used a specialized analyzer, the AMS 2140. The really big deal with this tool was its ability to measure vibration on 4 channels simultaneously, while also measuring the exact rotational speed of the machine using a separate tachometer input all at the same time.
Okay, 4 vibration points plus speed, all synced up. Why is grabbing the speed at the exact same instant so crucial?
Because most mechanical problems in rotating machines, imbalance, misalignment, shaft issues, bearings, create vibrations that are directly related to the rotation speed. Harmonics of it, fractions of it, etc.
Ah, so you need the speed reference to make sense of the vibration frequencies.
Exactly. Especially if the speed is changing, like during startup or shutdown. You absolutely need that simultaneous speed data, often from a attach pulse, for certain analyses like orbit plots or transient plots like the coast down we'll talk about. This tool made collecting all that synchronized data really fast, like a minute per machine.
Right, so they hook this up while the compressor train is running normally, steady state. What did the vibration data show?
Well, they saw the expected peak at the running speed frequency, which was 210 hertz. No surprise there.
Mm.
But they also consistently saw this other strong peak way up at 1900 hertz.
1900 hertz, that doesn't sound like a simple multiple of the running speed.
Not at all. And
Okay.
it's just there. Present throughout the steady testing on the displacement probes measuring shaft movement. That was their ghost frequency in this industrial setting.
Okay, so they see this weird 1900 hertz signal. How do they figure out if it's a genuine mechanical issue threatening the machine or something else?
This is where the simultaneous data and a specific diagnostic technique were absolutely golden. They performed a coast-down analysis.
Meaning they shut the machine down and recorded data as it slowed to a stop.
Exactly. And they watched what happened to those frequency peaks on a waterfall plot, which shows frequency changing over time. As the machine spun down, the 210 hertz running speed peak did exactly what you'd expect.
It slid down towards 0 hertz as the speed dropped.
Precisely, because it's directly tied to rotation. But the 1900 hertz peak,
What did it do?
absolutely nothing. It just stayed stubbornly parked at 1900 hertz for the entire coast down, even as the machine slowed to a crawl.
Whoa. So it wasn't changing frequency with the machine's speed at all?
Not one bit. And that was the key diagnostic finding. A vibration frequency that remains constant regardless of rotational speed is almost certainly not caused by a rotation-related mechanical fault, like imbalance or misalignment.
That's the smoking gun then. It proves it's not tied to the machine's rotation.
It really is. It told them this ghost frequency was something different.
So what else did they notice about this 1900 hertz signal?
Well, interestingly, it wasn't showing up strongly on accelerometers mounted on the machine's casing, the outer body, only on the proximity probes looking directly at the shaft.
Suggesting it wasn't like a typical mechanical vibration shaking the whole structure.
Kind of hints that way, yeah.
Yeah.
And it was present on all 4 identical machines they looked at. But here's the real problem it was causing. This 1900 hertz signal, this ghost frequency, sometimes accounted for a huge chunk, like up to half of the total vibration energy being measured by those shaft probes.
Okay, I think I see where this is going. The machine probably has a safety system.
Exactly. A protection system set to trip and shut the machine down if the overall vibration level gets too high.
And because this non-mechanical 1900 hertz signal was adding so much to that overall reading,
It could push the total energy over the trip limit, causing the machine to shut down unnecessarily, even if the actual mechanical condition was perfectly fine.
ouch. False trips are expensive. Downtime, lost production.
Major headache. So the crucial outcome of their analysis using that coast down data was proving this 1900 hertz signal wasn't a sign of impending mechanical doom, it was something else.
So what did they do or plan to do once they knew that?
Well, knowing it wasn't a direct mechanical threat allowed them to think strategically. Plans included things like double-checking how the protection system was set up, trying to find the actual source of the 1900 hertz signal, maybe electrical noise, external interference, something needing better grounding or shielding perhaps.
Makes sense. Hunt down the real cause.
Right. And also consider maybe adjusting the protection system's frequency filtering to specifically ignore that 1900 hertz signal, since they now knew it wasn't indicating a dangerous condition. Plus, obviously more analysis to pinpoint the root cause.
So the takeaway from this industrial case is pretty stark. Real-world machines can definitely have these problematic ghost frequencies that aren't linked to their basic operation, like speed.
Absolutely. And diagnosing them, telling them apart from real mechanical issues, demands the right tools, like that simultaneous multi-channel analyzer with speed and the right techniques, like the coast down plot. That's how you separate the ghosts from the gears, so to speak.
It's about having the right data, captured the right way, to see how signals behave relative to the machine's core function.
Couldn't have said it better.
Okay, let's try and weave these two threads together. We've got the physics lab showing that nonlinear systems, even simple ones, can inherently generate frequencies that weren't put in.
Driven sometimes by chaos itself. and heavily influenced by the system's own response characteristics.
And then we have the real-world factory floor, where complex vital machines can show these unexplained frequencies that mess with their safety systems, frequencies totally unrelated to how fast they're spinning.
It's kind of surprising when you put it side by side, isn't it?
It really is. Noise, the usual villain, can actually help reveal signals in the lab. Tailoring an input perfectly to a circuit's quirks makes a hidden frequency jump out.
And a multi-million-dollar machine can be brought to a halt by a signal that looks like damage, but is actually some kind of electrical or environmental artifact interacting with the monitoring system.
These aren't just like academic curiosities. They point to something fundamental about complex systems. They don't always just give back what you put in, scaled up or down.
No, they process, they transform, they interact in nonlinear ways. Unexpected things, like these ghost frequencies, can emerge from those interactions.
Which brings it back to you, the listener. Whether you're dealing with biological signals, designing electronics, managing networks, or maintaining machinery, the world is packed with these nonlinear behaviors.
Yeah, and the lesson is you can't always just take a signal reading at face value. You need to dig deeper. Ask, is this signal really what it looks like?
Does its behavior make sense in the context of the system's fundamental operation? Or could it be one of these ghosts?
And figuring that out takes careful analysis, often specialized tools, and that critical thinking to question the obvious interpretation. It requires understanding the system's potential for nonlinear tricks.
It's a really potent reminder that complex systems often have way more going on under the hood than you might initially suspect.
So we've taken quite a journey today. From the controlled chaos of Chua's circuit on a lab bench,
To the practical troubleshooting of unexpected vibrations in massive industrial compressors.
and the common thread really is this fascinating idea that frequencies can just appear seemingly out of nowhere.
Sometimes they reveal something deep and intrinsic about how the system works, like in the Chua's circuit experiments.
And other times, they signal a hidden problem, maybe interference or a system interaction that needs a totally different kind of fix than what the signal first suggests, like in the machinery case.
It definitely makes you think, doesn't it? What other kinds of ghost signals might be lurking in the systems all around us?
Yeah, from our own senses, our biology, to all the technology we depend on. What signals are there just below the surface, waiting for the right conditions or maybe just the right kind of analysis to finally reveal themselves?